This video is brought to you by the Maker Barn, a non-profit makerspace in Magnolia, Texas. At the Maker Barn, we can actually make our own prototype circuit boards, printed circuit boards, and we make it by taking circuit board material, copper-clad material, and using a small CNC milling machine and actually cutting away the copper to separate lands and that sort of thing. This is what we're looking at here is a circuit board in Eagle, and this particular circuit board was laid out on one side, is laid out on the bottom. Here's the bottom is blue, and you can see we all kept it all on one side. You can make two-sided circuit boards, but there's some more push-ups involved in doing that. So we'll just stick with this kind of thing right now. You can see that there's components. This is a through-hole board. You can make surface mount boards as well. It's depends, not fine, not super fine pitch, but normal, surface mount material works just fine doing this technique. Okay, so let's take a look. We've got through-hole components. We got all these traces that we want to have. We've got pads, and we've got all the pads have holes, and there's a couple different size pads, and so we'll have different size holes. We've got mounting holes here that are quite large. I think these are 110 mils, something like that, and we can make them for screws to go through. And we also have, what I've done on this board is I've done a copper pour, and the reason I did a copper pour is that our finished board will have copper in all these areas, but I want to make sure there aren't any isolated islands of copper that need to be tied to ground. So what I can do is I just did a copper pour used an Eagle. Now this will work. This whole process will work for virtually any circuit board layout program that produces Gerber files. KiCad would work, and other ones as well. Anyway, I'll turn on the copper pour, and and this is a good way to see it. What the copper will be removing from that surface of the board is pretty much like this black outline area between the copper pour and the actual traces. And if we ran the DRC on this, we'd find that it said everything's okay, and all of our ground connections are good, and there's none that are in isolated areas. So that's good. And so let's take and convert this to Gerber files. Any circuit board, if you want to do it, like with using a mini chop, or if you're going to set it out, it requires that you produce Gerber files, and we'll look at how that's done. We use this CAM processor. This is part of Eagle, and let's see, it wants me to save it. All right. So we get into the CAM processor. There's a few things that we do in here, probably a little bit different than if we were going to send it out to PCBWay or something like that. And one of those things is pretty important, and that is specifying that this is imperial. In other words, an inch. That the output, the Gerber files will be in inches, and that's really beneficial to us. If we say bottom copper, that's what we're interested in. You can see that it has the copper pour, has all our traces on it, this sort of thing. Now, one thing that's missing is the board outline, and we want to be able to cut that out with our machine. So I'm going to click this board shape down here, and that will give us our outline. It actually puts about a 10 mil trace around the outline, so we'll have to deal with that later. But anyway, so we got that. The other thing that we have to pay attention to is the drill file. We're going to be using the bottom copper, and we use a drill file because we want to know where the holes are drilled, and we can automatically drill the holes, which is really nice. The problem that we have here is that it comes out with a file extension of XLN. Exelon is what that would be for, and that's fine, except that CAMBam, the program we're going to be using next, doesn't like that. It wants DRL. So I'm going to backspace and call that a DRL file. And okay, So we've got everything done. We got this imperial. We've put an outline around our bottom copper, and we've got the auto drill thing fixed up. So we can process the job. It wants to know where we're going to put it. So I've got a little folder right here called test. Oh, we can put it in there. We'll select that folder, and it's done. It doesn't take long. Let's take a look at that folder. It produced another subfolder called CAM outputs. So we'll open that. You see assembly up here. The assembly one it could be handy. It's got parts list, that sort of thing in it. Drill files. We just have the one drill file, and it is .drl, which is good. If we forgot to do that in the previous step, that's okay. We can change it to .drl now from XLN. It was still XLN. And let's go over here and look at the Gerber files. You'll see a bunch of Gerber files, and the only one we care about is copper bottom. That's all we care about. We don't care about the copper on the top of the board or any of this silk screen and stuff like that. We're not going to do that. So that's good. So the next step is let's actually start converting those Gerber files into something useful for our mini chop. I've got several desktops open here, and two of the desktops are CAMBam. We need two versions of CAMBam. We need one version to load in the drill file, and the other version to load in the copper bottom Gerber file. So let's go. First of all, let's go to one of these, and we'll load in the drill file first. So we can file, and we're going to open up. Oh, it came right to the drill file, but it is in our test thing, our CAM outputs and drill files. So we want this drill file, and we open it up, and it looks pretty weird. Now, I think the reason this is weird is because the decimal point in the eagle is in the wrong spot. Now, I could probably change that eagle, but if it does, it may interfere with the stuff that's going to the board shop. So I rather not. I said I'll deal with it here. And the way we can deal with it was just select all these. Easy enough. This is our 0, point, by the way. This is our origin down there. So we'll just say edit, transform, resize, and set it at 1000%. It defaulted to 1000%. So I'll say apply, and there we are. So this is all the points that we're going to be drilling. These are the big holes in the outline, and then this is where the IC is, that sort of thing. So that's where all those holes are at. Now, what we want to do at this point is select all this, make sure you get it all selected, and do a Control-C. In other words, put that in the scratch pad. Now, let me open up another version of CAMBam. And in this one, we're going to go File, and we're going to open the copper bottom Gerber file and open that up. It takes a while to process this file because it's having to do this conversion, and I think this thing's written in Python, but so it takes a little while depending upon the complexity of the board's really complex, and it's going to take longer, of course. But it's thinking, there we go. Again, this is our 0 down here. That's a board outline. Notice it is two lines rather than one line. We'll fix that. You can see here all our traces, and our traces are buried in this copper pore. And the copper pore comes around. You see that? But let's get rid of that. Well, let's get rid of that copper pore. So I'm going to click that. You'll see it's called a region. It's called a region. And we're going to just select that and delete it. Say okie dokie. Now, the other thing we need to get rid of is we only want one outline. So I'm going to select this thing, and it too is a region. Now I don't want to delete the whole thing. What I want to delete is just one of those lines. The outside one is generally what I take off. So again, we edit and convert to polyline. So that'll convert that region into actually two polylines right here, 15 and 16. So if I select the outer one, and I'll deselect that, select the outer one, hit the delete key, and delete it. Now, all that's good. Now I can do a Control V, and that'll bring in the point list was from our other instance of CAMBam. And you can see it brings in all these points. There's 4 point lists. If you use different size drill bits, you'll get a different, additional point lists. So if you had 5 different sizes of drill bits that you use or drill holes, then you'll get 5 point lists. If you only had 1 hole for the whole thing, then you'd only get 1 point list. But we've got 4 in this case. And so anyway, let's do something else here that's really important. We're looking actually at the top of the board, and we're looking through the board, seeing our traces. Now that's not going to be too good, because if we were to go to etch this, then we would essentially etch the bottom side of the board on the top. That might be a real problem for us. So what I want to do is select the entire board, make sure you get everything selected, and then come in here and do an edit, transform, mirror, and pick one point on the on the X origin there, on the X-axis, and pick another point there. Boom, it copies it. So we've got it not only mirrored it, but it copied it. So we've got to get rid of all this stuff, and that's dealt with by. Well, let's see. Let's try it this way. If we select it this way, we can get most everything we need, and we'll delete that. And then this thing, we'll just select that and delete that. We don't want to delete anything over here. All right. So here we are. The board is flipped over, and and remember, this is the 0, 0 here. So keep that in mind when we go to machine it on the machine. So let's first of all talk about what we plan to do. What we're going to do is, like if you're using our normal CNC router, you know that if you use a particular tool, you really want to do all the operations as possible with that tool before you change to another tool. So we're going to do that. We've got an isolation tool, which is a tiny little 60-degree V cutter, and it's solid carbide, cuts this copper and fiberglass like it was butter. And so what we want to do first off is cut the separation lands. We want to separate these from the rest of the copper. Then we want to come in and make some little dimples at each drill location with that thing. That tool is very, very stiff, and if we come down and make a shallow dimple in that, it will be exactly where we need it to be. So when we come with the drill bit, which is kind of, it's a skinny little flexible, sort of flexible drill bit, we want it to not walk around on the surface. We want it to be right in there, so it'll fall in that little divot. Now the other thing we want to do with the isolation tool, the first tool there, is we want to cut a little V groove around the board. And that V groove, what it does for us, you don't have to have it, but what it does for us is it makes the edge much nicer. It bevels it a little bit and makes the copper edge much nicer. So, so let's first off do our trace separation thing here. So we can select this polyline, shift, select all the polylines here. That selected the outside one too. Let's see. There we go. I don't want the outside, just the traces. So we got all the traces selected. Oh yeah, before I do that, let me do one thing I should mention is that if we we want to set up a couple of things. If we click on machining, where it says basic and advanced, if it says basic, it's in advanced mode. If it says advanced, it's in basic mode. So we want to be in advanced mode. We come down here to post processor, and we can select our post processor, which is going to be called default. And the default puts out a generic G code, which is what our mini chop wants. Also, we need to select the tool library we're going to use, and that'll be PCB routing. So once you select those things, then we can come back in here. We still have all these selected, so we can do a profile. Now, profile, what it does is it doesn't cut on the line. It won't cut on the line. It cuts alongside the line. And knowing the diameter of the tool, it produces just the right offset. So it cuts along the outside of that line. And this outside is right here. Now, if we said inside, that'd be big trouble, because then we would be cutting away our trace itself. So we'll say outside. We're going to say give it a target depth. Now, this is a depth, so it's going to be below the surface. So we have to make sure we call it minus. Put minus 0.005. In other words, our target depth is 5/1000ths of an inch. That's not very much. Just a little bit more than the thickness of a piece of paper. Don't make it 50. Don't make it a ½ inch. Make it 5/1000ths. Make sure you have enough zeros in there. All right. Most of the other things we can take. We need to come down here, and we definitely need to change the spindle speed. We'll have to do this on every operation to 24,000. We want it to go as fast as it can go. And then we come down here. We want to do cut width. Let me do this machining, and if we do a toolpath, yeah. Oh, I haven't finished it at all. So anyway, let me go ahead and specify tool number, isolation, and do the toolpath. Machining, generate toolpaths. Now, if you look close, you'll see it's really making just one path across there, and that's fine, but actually it's a little narrow. If we try to solder on here, for instance, we have very little distance from the trace to the copper that's left on the board. So let's come in here and cut width and make that 0.016. That's the number I usually use. I hit enter, and then what I'm going to do is generate the toolpath again, and yeah, see how it'll come by and it'll make another pass. And this also is good to prevent little flakes of copper from shorting things out. It's a good idea. So not strictly necessary, but it's good practice. All right, so we got all our traces cut at this point. Now let's put in our little dimples. So we come back up here and we get the point list, put shift, select, and I'll get all our point list. And then in this operation, we're actually going to do a drill. We'll do a drill, and we come down here, we'll do a target depth of minus 0.015. 15/1000ths of an inch is good. You could go a little deeper, go a little shallower. It doesn't matter a whole lot, but that's just a number that's kind of nice. All these other things are okay. Come down here, we definitely need to change this to 24,000. All right, 24,000. And the tool number will be the same, isolation, number 1. And we could go back up here, machining, and generate the toolpath, and you'll see that all those get, so you can kind of see that all these are going to be cut. Let's see, last thing we're going to do with that little tool is do this outline that we're talking about. So let's highlight it, select it, and we're not going to do a profile, we're going to do an engrave. An engrave means it's going to go right on top of that line, not offset from it, but right on top. And it defaults to minus 15,000, so that's kind of handy. Don't forget 24,000 down here. And the tool number, again, same tool. So when you load the isolation tool, it's going to do all these operations, and then it'll stop and ask you for another tool after it's done with these operations we've done. So that's kind of nice. All right, so at this point, we've got our traces cut out. We've got the drill locations spotted, and we've got the outline just cut a little bit, just beveled down a little bit. So now we need to do some drilling. And one thing that we can do, we can select one of these points that we know is on a circuit board, for instance, let's say, or for discrete components. We select that, we get a bunch of these things. Now, there's another, that's the point list 35. Now there's as I recall for this thing, there was, over here. This was a diode, and for some reason brought up a different drill size. Now what the drill size that we use for the IC over here and all these other will work fine for that diode. So I'm going to go ahead and click that. Oop, I should have hold Control and click it. So now we've got these 2-point lists because we want the same size hole for all those points. And all right, so we've got those selected. Let's drill them. We're going to drill, and we're going to go target depth minus 0.075. This 75 thousandths is important. This will bring us down through the circuit board, past the bottom of the circuit board, and just barely into the vacuum platen, but not very much. So we don't want to destroy the vacuum platen. We're trying to make that 75 thousandths. Now, if you were a thinner circuit board, so I got 031, then you probably want to come down about 45 thousandths or something. But just don't make big holes in that. Okay, and then let's see. We're going to just use a can cycle. That's the default, so that's fine. Can cycle is it does the whole process. And again, what do we need here? We need 24,000. Spindle speed, really important. And the tool number. Now, these holes need to be about 31 thousandths. And as it turns out, 31 thousandths is 0.8 millimeters. You can see we have tools that come all the way from 0.3 millimeter up to 1.2 millimeter. But what we need for that hole is probably about 0.8 millimeter. So we'll select that. And then we can go to our generate toolpath just to see if, yeah, okay. And you can see the diameter of the hole there. Looks about right. It's unfortunate Eagle doesn't leave a whole real big pad, and so you have to be a little careful about that. But our system is quite precise. So we got that. Those are all drilled. Let's go ahead and drill the next size up, which would be these holes right here. And that's point list 33. And these are just the 25 mil square posts. So we need a little bit bigger hole, maybe a 35 thousandths for that. So we selected those. Let's do a drill. Come over here, target depth. What's the target depth? It's going to be minus 0.075. Okay, no deeper. And you don't want to go less because it won't drill all the way through the board. Again, can cycle is fine for this because we're just going to drill a hole, easy enough. And what we put here, we have to put our 24,000. And then we have to specify our tool number. Now these are going to be 35 thousandths. So that, it turns out that's a 9mm. So we come down to our tools, we select a 0.9mm, and we're all set there. Now we can drill. Now it knows, and we can select the toolpath. I usually do a select toolpath, not that it's needed. It's just kind of like an assurance that okay, that tool is finished. We finished defining that. Now this will be an interesting thing. The next will be this point set out here, the 4 mounting holes, and we're going to make those say 110 thousandths in diameter. Now we don't have a drill that's that large, so what do? Well, we're going to, instead of drilling that hole, we're going to route it. And so let's see, we'll still call it a drill. We've selected those points. Now we're going to call it a drill. And what kind of target depth we're going to go? It's still going to be the same. Minus 0.075. Okay, 75 thousandths. We're going to not do a can cycle this time because our routing bit is only 50 thousandths, yet we're going to make a hole 110. So I'm going to say, instead of can cycle, we're going to go with a spiral mill. Clockwise or counterclockwise, I don't know, it makes a whole lot different. I just usually pick clockwise. And the hole diameter is going to be 0.110. Okay. That's it. And all these things are all right. What we need is to make sure, okay, I always have to look for this, 24,000. If you did it at 1,000, it would probably break the tool. And the tool number. This is going to be a little bit, right at the bottom there's an end mill, 50 thousandths end mill, so we'll select that. And you can see on the thing now we've got some large diameter holes. All right. Now, the last operation we have to do is cut out the board. Now, our mini chop uses a vacuum platen. It holds the circuit board down really well with vacuum. So if we cut this out, we really don't need tabs. If you're going to make real small circuit boards, you might want to use tabs because there's not enough surface area to hold it in place real well. But a circuit board this size, we won't bother with tabs. But we can just select the outline, and we're going to do a profile again because we want to be on the outside. And we're going to say a target depth of, right, we're going to use what? Minus 0.075. None deeper. Please don't. We need to set the speed. Remember that? 24,000. Okay. And cut width will be determined, that's by the tool, so that's not a problem. Tool number, and we're going to say the end mill again. And when we do our sharing toolpath, we'll be able to see that. So I'm going to zoom in here. Notice we've got 2 tracks on the outside, or two passes on the outside with the little isolation tool. And then out here we've got a single pass. And one thing I wanted to say is that you might want to, if the default depth increment is 15 thousandths. Well, that would take quite a few hits, like what is it, about 5 passes to cut it. So we can actually change this to 25 thousandths. So we can come down 25 thousandths on each pass. That way it means there's only 3 passes to get to full target depth. Again, that's not super necessary, but it does save you time. And that's the deal. Remember the origins down here. We're going to do a machining operation. We're going to do a produce G code. And what I'll do is I'll just put this in the same desktop test. And I'll just put it right here. Now you can change this, the name of it. It defaulted to copper bottom because that was a Gerber file we brought in, but we can call it something like, let's call it test PCB. How about that? And save it. And that's it. And that will be the file that we'll be using for the mini chop. And that'll be in another video because this one's awfully long. So let's do a little review. There's a lot of steps to this. So let's just take a look at what we're doing. We were working from Eagle. Of course, other PCB programs would work as well. But in Eagle, we would select the CAM processor. We'd set the units to imperial or inches and turn on the board shape for the bottom copper. Remember to do that. Set the extension of the drill file to .drl, and then process the jobs, which produces the Gerbers in a drill file. So to use CAMBam, we're going to open 2 instances of CAMBam. One will be for the drill file, and the other will be for the actual routing, etching of the circuit board. In CAMBam number 1, be sure it's set to inches. Load that .drl file. You may have to resize it to 1000%. If you're bringing it from Eagle, that'll probably be necessary. And then select the whole thing, all the point lists, and do a Control-C. In other words, just save it to the clipboard. And then the second CAMBam, make sure it's set to inches again. And open the copperbottom.gbr file. Now this is, of course, if you're doing the bottom of the board. If you're doing the top of the board, then open the copper top one. Anyway, let's see. Type a Control-V, and that will insert the point list for all the hole locations. That will one thing to remember, and you should not have closed CAMBam number 1. Okay, if you closed CAMBam number 1, you'll lose that information. So anyway, then let's delete the copper pore region. That's the region that we made back in Eagle. We made the copper pore, but we get that out of the way. And then the outline, if you notice, it's 2 lines, and it's actually a region. So we're going to use the edit and convert that region to polylines, and then delete the outer outline so that we only have one outline that you have to deal with, only one line around it. Mirror the entire board. Remember, select the entire board, use edit and transform mirror function to essentially flip it over so we can work on the back side, and then delete the old version of the board. It actually produces a copy, so we want to get rid of the old one. And then go to the machining and set the post-processor default and the tool library to PCB routing. That's important to do for us later on. Now, the first tool we'll use is actually tool number 1, the isolation tool. This is a little 60-degree short little tool that will cut a V profile in our board, and we can use it just like the traces. So we're going to select our traces first and set the cut depth to minus. Remember, it has to be minus 0.005, 24,000 RPM with 16. The width of 16, remember, that gives us the two paths. So we have a little bit wider cut, and to select, of course, tool number 1. Then after we do that, then we're going to dimple each of the drill positions. So we'll select the point list with the drill, with the all the point lists, and set the and then with the drill operation, set the depth to, again, minus 0.015, 15 thousandths of an inch. Set spindle speed 24,000, and of course tool number 1. And then select the board outline, and we're going to do an engrave operation just to bevel the edges of the board. Again, set the depth to minus 15 thousandths, spindle speed of 24,000, and tool 1. These are all done with one tool, and you don't have to do a tool change in the middle of this. All these operations be carried out one right after the other. Now for drilling operations, for holes less than 50 thousandths and smaller, right, 50 thousandths and smaller, this is what you would do. You'd select the point list for that desired hole size. So your board may have several different hole sizes, but select a point list for a particular size, and then in the drilling operation, set the depth to minus 0.075, in other words, 75 thousandths. And that's for 062 PC board material. If the board material is thinner, set it less depth. If it's thicker, set more depth. But we don't want to damage the vacuum platen under the board, so that's why we set that speed, that depth. Spindle speed 24,000 as usual, and then select a tool for your desired drill size, and that's 0.3 to 1.2 millimeters. And then you repeat this operation for each of your drill sizes. Now, if your drill's holes, like a mounting hole, is larger than the 50 thousandths, then we're going to change the operation from a can cycle to a spiral milling cycle. And so we, like we did before, we selected the holes, the point list for the desired hole size, in other words, mounting holes or whatever you might have. Sometimes you have to have a large hole for mounting like a 7805 or something like that, voltage regulator. Set the depth to, again, to minus 0.075, 75 thousandths for the 16th inch PC board. And the drilling method, when you're in the drill operation, drilling method, select spiral mill clockwise or counterclockwise, but clockwise seems to work well. And set the hole size, next part down, to your desired size. So if you wanted a hole that was a 1/4 inch in diameter, you could say 0.25, and it will do it. Set the spindle speed to 24,000 and use tool number 30. The tool number 30 is the in-mill tool that we typically use, and it's 50 thousandths in diameter. And for cutting the board outline, oh yeah, I wanted to mention that you should always save those hole milling operations for last, because the last tool we use is going to be the end mill. And we select the board outline, do a profile operation, make sure it's an outer profile, set the depth increment to 25. The default is 15 thousandths, which means it would take more passes to do the job, take a little more time, so 25 speeds things up a bit. Set the depth to minus 75 thousandths, again for 62 mil 1/16 inch circuit board material. Set the spindle speed to 24,000, and set the tool to number 30, the end mill. So that should do the trick, and next thing you'll do is generate the Gerber operation, the G-code operation, and we'll be able to take that to the machine and machine your board. Thanks for watching.